Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure for me to welcome Carlo Carino from Politecnico di Milano and by way of UCLA, who will talk to us about some combination of temporal databases and schema evolution. The system is called Panta Rhei. Carl.
Thank you very much for the introduction. So I will present you part of my PhD thesis, which is exactly about database evolution. So our motto is Panta Rhei, which means everything in a state of flux. And this is particularly true for the business reality, which is continuously changes and forces the information system underneath to continuously adapt to evolving requirements. And this has been studied as a bad problem. Evolving software, evolving information system, it actually costs a lot. It can cost up to 75% of the overall cost. And as a database person, I focus on the problem of the evolution of the data management core of an information system. In particular, I concentrate on the issue of schema evolution, and so how we can try to better support the applications when the schema needs to change. And the problem of archiving the content of a database, for example, to meet the accountability obligations of a company. And of course, when you evolve, one of the things a company continuously do is merge and acquire each other. And so you have to integrate the information system, and at the data management level, this often ends up being a problem of data integration or related data exchange and similar. So during my PhD, I had the great opportunity to visit Professor Zaniolo for over a year and a half at UCLA. And in fact, my thesis is a little bit on two sides of the Atlantic Ocean and two sides of the problem. In Politecnico, I work on data integration and data extraction with an approach based on ontologies, and some work on context-aware data filtering. And in the lab of Professor Zaniolo, I work on the problem of schema evolution and database archival. So today I will not have time to talk about both, so I will focus on the problem of evolution in databases. And of course, I'm available if you want to talk later in the meeting we have about the rest. I will be happy. So the problem of schema evolution, it's a well-known and long-standing problem, and traditionally it's been very difficult to understand exactly, at least for the researcher, especially for the academic researcher, to exactly understand what's the overall impact of evolution on a database, and what characteristic has this type of evolution. So before starting the actual work on schema evolution, we decided that there was needed some better understanding of the problem. So what we did is analyze information system. Luckily today there are web information systems. Some of them are open source in nature, like Wikipedia. So we had a good set of information about what they were doing. Wikipedia is a popular website and has a relational database backend that actually stored the entire content of the website. So it was a good example. It's very popular. Everyone knows about it, and it's open source. We can both get the data and release the information that we obtain. And we discovered it was actually a pretty interesting case. We had over 170 schema versions in 4.5 years of lifetime. And there was also a big need for archiving the content of the database. They actually need a transaction time database, even if they probably don't say it in the same way, because about 30% of their schema was actually dedicated to timestamping the content, maintaining archived version of the content, or deleted version of the images, etc. And so what the use of this work has been to assess the severity of the problem itself, and to, in a sense, guide the design of our systems, in particular of the language of schema modification operators that, as I will present, is quite central in our work. To give you an idea of the analysis, I post a couple of the statistics that we can collect from the Wikipedia case. One was showing the schema sites in terms of the number of columns in each version, in each subsequent version. So you see it goes from about 100 to 250, so it's growing quite a lot. And this goes together with the popularity of the website and all the features that have been added little by little. And on the other side,
So what's the cause of the dramatic downward?
the spikes. Okay. That's the problem is that even in the publicly released schemas, which are the one we are using, not the internal development one, sometimes they have synthetic mistake in the schema. So the actual script that is supposed to load the schema will not actually work, and will only load some 2 or 3 tables there, and so it's end up having this spike like this. I left them there because in a sense they represent part of the problem of evolution. On the other side, I show what's the impact, what can be the impact on the application. So what we show is the query success. If we take a bunch of queries that used to run and were designed for schema 28, and we try just to blindly execute them in the subsequent schema versions. And as you can see, there is not much success in doing that. It means that even a little bit, few differences in the schema can actually break a lot of queries. And these represent part of what we want to try to solve. So the Wikipedia example was very useful for us and give us a lot of feedback. So we decided to go a little bit beyond Wikipedia. We developed a tool suite to automate the collection of this kind of information about the evolution of a system and to run analysis on top of that in an automatic way. And the process at the moment is collecting a very large data set of this evolution history. At the moment, we are around 180 evolution histories from scientific databases like the Genève CERN, the Nuclear Research Center in Genève, and several genetic databases. Of course, open source information system, some administrative databases from the Italian government. So the idea is creating basically this big pool of real examples. And to use this for benchmarking tools that support schema evolution and to have a clear idea of what's schema evolution. At the moment, we are planning to survey about 30 open source commercial and academic tools around to create a good picture of what's the problem and what are the solutions. And I guess in general, this kind of data can be useful not only for benchmarking schema evolution, but in general for creating benchmark and having feedback. For example, for the idea of mapping composition, the benchmark that Phil Bernstein was suggesting in one of his recent papers can probably be based on some real data and trying to see how the various tools would do, mapping composition tool would do to try to follow the evolution that happened in these cases. And of course, we're going to release everything for public use. So let's see how we try to solve the problem now. Now that we analyze the problem and it looks pretty clear what it is, the Panta Rhei Framework is the effort that we're doing at UCLA for solving the problem of evolution. So there's 3 main systems that collaborate tightly to solve this problem. One is the system PRISM that is the first one I will present, and I will give you a short demo of it, which basically supports schema evolution for snapshot databases, so like regular databases, and use schema mapping and query rewriting to support that. The second system is called PRIMA, and basically add archival functionalities on top of what PRISM is capable of doing. And there is a bunch of optimization we have to put in place to actually be able to make things running fast enough. And the HMM sort of complement the other two by maintaining the sort of a documentation of the evolution, so metadata histories, and allow temporal queries on top of the metadata history. This can be useful. So let's see, schema evolution. We typically start from a database DB1, his corresponding schema S1, and a bunch of queries Q1 that run just fine for our business needs. But we need to store more data. We need to store data differently to be faster, for example, support new functionalities. So we need to move to a new schema S2. So what typically happens is that the database administrator will write down some SQL script that changes the schema, some other SQL script that migrate the data from version schema 1 to schema 2. And the application developer will probably need to tweak their queries to run on the new schema. And this is what typically happens today. Unfortunately, this is happen again and again and again. So we have this kind of process happen every time we change the schema. To give you an idea, Wikipedia, we said 170 schema version. If you go toward the scientific databases, the ensemble genetic database, they had 410 schema versions in 9 years of history. So this means about a schema version every week or every 10 days. That's a little bit too much. I mean, it's a lot of reworking of the query. especially because in the case of Wikipedia, here say the impact on queries, up to 70% of the query need to be manually adapted after each evolution step. This is like the worst case, but it means that if I have hundreds of cases, it means I'm doing a lot of work. And also is a problem for the data migration, because every time we do data migration, there is a risk of like losing data, because I did something wrong in the script that migrates the data, or there is I might create redundancy. And even the efficiency of the migration, if you talk with the people that work on astrological databases, they say that even adding one single column might take weeks, because they have petabytes of data in each table. So even the migration might be costly. And the efficiency of the new design is also at stake. How fast will run my queries on the new design. So what we would like to be the schema evolution, we would like to have the design process itself to be somewhat assisted and predictable. So have an idea of what will be the outcome for data, schema, etc. The data migration scripts, we don't really want to take care of that. Let's have some tool that generate them. And legacy queries would be wonderful to have them somewhat automatically adapted to run in the new schema. And the same goes for views, updates, and all the rest of the objects that we have within a database system.
This ideal world is presuming that when you move from database to database, it's monotonic in terms of the information content, right?
No, not needed to be. It might be that some
Query Q1 talks about something that you decided not to store anymore. There's no way it can.
In that case, you cannot support query Q1 anymore. But that would be the user choice. If I decide that, for example, I have a query that asks about engineers, and I fired all the engineers in my company, at that point I don't need to support a query anymore, right? So this is more or less what we try to do with our system. So general view of the PRISM system. So to support schema evolution, the evolution design, we define this language of schema modification operators. It's not a new idea. We just try to make it working in our examples. And by analyzing this language, we can foresee what will be the impact on the schema, on the data, and on the queries. To automate the data migration, we just generate a SQL script out of this language. And to automate the query support, we will derive a logical mapping, so correspondences between subsequent schema version, and use this information to do the query rewriting. And the current work is basically try to make the same work working also for the updates. And so having a better understanding of the integrity constraint and propagating them and see what happened for the updates. And it's a little bit more tricky. So the language we have, schema modification operators, each operator represents an atomic change. And by combining them, we can create complex evolution steps. And the idea is that they've been designed and tested on the Wikipedia example, and they cover the entire Wikipedia example. And if we try to apply them to the other cases we collected, we have a coverage of the evolution step of about 99.9%, which I would call it a success by now. And we will see later how we can try to make it to that like 0.1% more. And so the idea is that each operator works both on the schema and on the data. So when I say join table A, B into C, I mean create a new table C, populating it with the joined of the two input table, and drop the two input table. So from a data migration point of view, the idea is that each operator is fairly simple and compact. And what we will do is just having an SQL script that implements in the system what the semantics of our SMO is. There is some optimization issues. We try to do some optimization at the single SMO level. And there is more work that can be done considering sequences. So if you add and remove things, or if you do multiple renaming, you can probably try to optimize there further. And from logical mapping, so the idea now is I need to do query writing. I basically need to have some logical representation of what's the relationship between subsequent schema versions. And at the moment, what I have is the input schema. I have the SMO, and applying it, I can have the output schema. And what I will do is basically taking looking at each of these SMO and try to see what's the correspondency that they generate between input and output schema. The language we use is disjunctive embedded dependencies. It's a fairly powerful logical mapping developed by Alin Deutsch and Valtanen. And the idea is that basically this is the minimum language we need to cover all our SMOs. And we will see how we use it for the rewriting in a little. So in this case, for example, I've joined table R and S into T where some condition. I will write two DEDs like this. One says basically, I will find in table T what was in table R and table S and satisfy a condition. And the second one basically just saturate the first one and says that in table T there is only what was coming from table R and table S and satisfy a condition. So we create an equivalence mapping between the subsequent schemas. So based on this language, we can say that we have a mapping M that relate the two schemas, and we can define our query answering semantics. So let's say that the database D2, first of all, it's basically what the database D1 migrated by this mapping, plus or minus whatever update comes into the new schema. Okay, that's the starting point. And what we want to do is now answer the query Q1 over the database D2. Problem is that query Q1 is on schema version 1 and database D2 is on the other schema version. So we have to find a way to connect them. We can assume we have an inverted mapping M-1 that will bring the data back under schema S1. So if this is true, I can answer, my query answering will be execute query Q1 on the version of D2 which is being migrated back. This sounds just fine. It's what we want to achieve. The problem is that I will not really migrate the data every time I have to answer a query. We can think about materializing. The problem that ensemble genetic database, I will not materialize the database 410 times, and every time I update it, I have to propagate the update throughout, all the previous versions. So this is just what we want to achieve. How we will achieve it is trying to find an equivalent query Q1 prime that, if executed directly on top of D2, will produce the same result of executing the original query Q1 on the version of D2 that has been migrated back. So this is our job, finding this query Q1. And the problem is that we actually were assuming to have an inverted mapping M-1. The user is giving me the mapping M, which is the one forward. Now I have to invert it. DDs are not really friendly for when it comes to invertibility. It's been studied recently by Fagin et al. And this language is a little bit too powerful to do inversion. So what we will try to do is inverting the SMOs and then deriving the inverted DEDs. And this works because the set of DEDs, we need the entire power of the language, but we don't use all the construct of the language in all the places. So the idea here is the following. When we have to invert SMOs, there's still a couple of issues. One is that not every SMO has a perfect inverse. As you can imagine, if I drop a table, there is not much I can do to invert it and go back to the exact same database. So what we need to do is using the notion of quasi-inverse, again introduced recently by the IBM group. And the notion of quasi-inverse is something like intuitively the best we can do, meaning whatever data we lost is lost, but we will try to bring back everything that survived the way forward. We will try to bring it back. That's more or less the intuition. And
sounds like an elastic definition. The best that you can do might be better than the best that I can do.
Yeah. No, the definition is it's a little bit more formal than that, as you can expect from this group of people. But
we don't set it that low, David. Before you go down this path, why not process the query by treating mapping M as a local as view mapping, and then just use answering queries using views as the? Would you come up with a different answer than doing it this way?
One of the opportunities that we have is actually once we invert the mapping, using that information to generate views and exactly supporting the original query using views. The idea is
that would be a global as view solution, though.
Yeah, because we use the inverse to support it.
Right. I'm wondering whether to come out with a different result than just simply directly applying a query to the lab, to M treated as a lab view.
Thinking about if there are issues like equivalence versus the general data integration approach, which just requires sound. I think it might do. I haven't considered that. So the other issues was that not every SMO has a unique inverse. So, but think about this. We are at design time here, so we can still ask the database administrator to help us and to disambiguate the cases in which the inverse is not unique. So just to have a couple of examples, quasi-inverse, for example, you have a join table R and S into T, and let's think that this is a join in which not every tuple in RNS participate the join. So I'm losing information by doing this. But I can use the decompose to go back, and whatever data survive the join will be redistributed into table RNS. The actual definition of quasi-inverse means that if now I decompose the data back, if they bring them forward again, I will lose nothing more. So I will obtain the identity on the target now. About the multiple inverses, one of the SMOs is a copy table RNS, R into S, and so we create 2 copies of the same table. And now, how to go back? It depends on what we do with these 2 tables. Okay, and the database administrator will tell us what's the use of these done by the application. If I have some guarantee that they are perfectly redundant all the time, then it's enough to drop the table S, and I will go back to exact same database. If the table R is sort of an old copy and table S is the one on which actually new interesting data comes in, then probably the DBA want to drop the table R and rename S into R because you want to bring back the data. Or if both receive interesting material, we want to merge them, so union them back to the table R. And this depends, choosing between these depends basically on what will be the semantic also of the rewriting. And so how we're going to support the old queries on top of the new database. So when we have the inverted SMOs, we can derive the inverted DEDs, which now specify the relationship in the other direction, so from the D2 towards D1. And we can use this information by means of using a technique called chase and back chase that will basically is going to add atoms to the query and remove atoms to the query, guaranteeing the equivalence. And of course, we will not do it randomly, but we will try to add atoms from the query is expressed in schema S1. Now I will try to add atoms that are from schema S2 using the mapping that I have, and I will try to remove atom from S1. And if I succeed to get the query completely expressed only on S2 and still be equivalent, then I succeed doing my rewriting. So the chase and back chase has been studied by Paul Patanen and Deutsch. And in fact, we use Mars as a query writing engine. It's a highly optimized implementation of the chase and back chase. It's developed at UCSD by Alan Deutsch, which is also co-author of some of our of the papers of the Panta Rhei Framework. And so we use Mars to do this query rewriting. So what are the issue here? From an implementation point of view, we have a web Ajax interface that support the database administrator during the development. It will be demoed at CDE, and I have a preview of this in a couple of slides. And at runtime, what we can do is support the queries as online query writing, or as I was anticipating before, by creating composed views that go from the schema S1 to schema S2. To create these, I will use the same query writing engine, but I will use it at the design time. I will issue some queries, something like select star from table, and I will rewrite that into an equivalent query in the target database. And now I can just set up a view that is the table that I have, and the body will be whatever the rewriting is. And so in this way, I don't need to trust my research prototype tool to run at runtime to support the application.
So what happens if you try to generate that view and M was not invertible? What kind of view comes out? I mean, do you give up, or do you just produce a best effort view?
No, the chase and back chase, either I can make it for an equivalent or you just give up, basically. That's the idea. And I know it's different from what you can do with the system that we were developing, which can materialize part of it on the way. And yeah, definitely from this point of view, either you obtain an equivalent query or you just cannot support the queries.
Long term, I mean, if you evolve a database, short term, obviously it's great if you can take your old queries and run them against the new database. But at some point, you've got to translate the queries.
Mm-hmm.
I mean, this can't go on. You can't keep running it through a rewriting engine every time.
Yeah.
Presumably you do need that. You do need to do the inverse and produce the view and be able to modify the queries.
To me, the idea is that this can be a tool that basically support the work of also the application developer. So the idea is that you will have to do the rewriting yourself if you don't use a tool like this. If you use the tool provides a suggestion of how you can do the rewriting, and probably what you want to do is to check the rewriting, make sure that it is optimal and works fine for you, and probably embed directly that new query inside your application. So you can try to say that completely transparently for the application will keep working. But most probably what will happen in a real scenario is that people want to see what this rewriting is, and that just will speed up the process of migrating the applications. That's my view on
Your
this.
experience of the rewritings comprehensible by humans?
Very much, very much. And because the Mars rewriting engine has been born as an optimization engine, so what it also does is removing extra unneeded atoms and trying to squeeze it down. So the result I've had on the Wikipedia, I will show you with the tool, but they make sense. The only funny thing is that, I don't know, for example, the aliases chosen for the table will be x0, x1 instead of something more meaningful for a human. But if you accept this little thing, it's more or less reasonable.
Can you give it a try to derive the names for the new tables from the old ones?
I would say it's just enough to use, for example, the initial of the table and make it unique somehow. So, and if it's already unique, you say table page as P instead of as x0. So when we finished the system, we were like, okay, how we can test this? Okay, how we can make sure that actually works? So we make tests on the again. We use Wikipedia and we used all the schema of Wikipedia. We use the query. We had access to an online profiler that actually provide the actual query running on the Wikipedia installations. We extract templates from that queries and we basically run those. And we use the data they actually released to make the rewriting, the execution time measurement. And we have two things that we want to make sure. One is that the system actually cures a lot of queries, and it's actually capable of rewriting a lot of queries, and that the rewriting is actually decent in speed in the overall result. So for first good news, 97.2% of, yes?
I was just wondering if the downward spikes in the left graph there correlate with the downward spikes in the previous graph.
They are exactly correct.
They're exactly the same.
They're exactly the same, yeah.
Okay.
And I just interrupt them there, not to make the graph looking too funny, but also the rewritten query will, of course, spike down there because there's no schema to run on, and the system will complain.
That's not simply a dotted line. Those breaks have significance with the spikes below.
Yeah. They are perfectly aligned down there. It's just Photoshop on the final picture. So the idea here is the following. 97.2% of the evolution steps are completely automated by the system. So every query that can be rewritten will be rewritten by the system. And in the 2.8% of the cases in which the system didn't succeed, it actually was able to deal at least with 78% of the queries in the group of queries that need to be rewritten. So it means that we're basically taking care of most of the work, and the user will be focused on a small portion of the actual of what he was doing by hand before, which is already pretty good. And that, just to give you an idea, that small queries that the user can rewrite are actually a situation in which he's just using domain knowledge and knows that he's dropping a table somewhere, but the same information can be also found if we correlate other two tables in an absolutely funny way. So I don't think there is any way to go. So we will not be able to improve this number for a while at least. And the other question was, how good are the rewritten queries? Fairly good news. The actual rewritten queries are very close to what the user can do by hand. So the execution time measured on one of the databases released by Wikipedia is actually fairly close to the one done by the user. And this gap in performance actually we check. Okay, and here that's the average over there. And the gap in performance is especially for query 13 and maybe for these other queries. There's a couple of cases. And the problem there was the following: the user was actually using some information about an integrity constraint that was not specified. You can think something like a foreign key that was not explicit in the Wikipedia schema. And at that point, he was using that to remove joins from the query. So if we try to put that integrity constraint explicit, we feed it in our query rewriting engine, the rewriting engine would do the same simplification and achieve basically the same performance, or almost undistinguishable from the one obtained by the user. And that was good news. We were quite happy. And so we wrote a demo that got accepted at ICDE, and I will give you a short overview of the system. Okay, I think it looks good. Okay, so this interface is a little bit between something meant for a demo at the ICD and what an actual tool will look. So there are things which are definitely academic and things that probably might be useful. So starting point is just running some configuration parameters like the database to connect to, what's the schema we're going to work on, and what's the schema where we're going to store the result of our work. And the first interesting part is this. And here basically I see what's the schema. And I can issue SMOs, so modification to that schema, and see what's going to happen. And the system helped me in doing this. So let's say, for example, I start from something simple, something like rename table archive into my archive. And the system will show me that table archive will disappear, and in the final schema, I will have a table my archive. So let's say I like that. And for example, I'm crazy. I want to drop the table page from Wikipedia. This means that the entire Wikipedia will stop working, but let's assume that's my goal. And the system says the syntax is fine, but pay attention, because drop table is not information preserving. It's like saying you're crazy, but it's a little bit more polite than that. So we drop the table page. And I don't know, we, for example, can copy table blobs into blobs2. And now it's telling me copy table. Well, it's pretty obvious, but it's generating redundancy here. So go ahead if you want. And I want to go ahead, and then I'll show you an example of, let's say, decompose table text, which contain the text of Wikipedia, into T1, and I put the ID there and the actual text, and table T2, where I put the ID, and the flags, which are random other attribute. So I throw it in there. And again, here appears T1 and T2. Now I have to go to the next part and see what happened to the inverses and what the system can do with this. So what the system does is, for each SMO, it tries to come up with an inverse. And so, for example, rename table archive into my archive, it does the opposite, my archive into archive. It's fairly obvious. For the drop table page, it would say, well, I mean, the data are gone. We cannot do much with that. But at least we have the same look in the schema. We would create an empty page, an empty table page with the same attributes. And copy table blobs, here it suggests a merge of the two tables. Of course, I can override this and say, no, drop table blobs too, for example, because I know that the two will be just redundant. And the decompose is come up with a join of the two. In this case, it's using the common attribute to make the join. And what we're doing now is being a little bit more specific with the integrity constraint. So it can also tell you you need more. You're missing one foreign key to make sure that the actual join will do the right work to bring back the data, and so on and so forth. And here on the merges union, yeah, it's a pretty good choice for the name, I know. No, yeah, merge is basically doing a union. So here it shows me. Given a query workload that I give in input and was preloaded in the system, but what it can do, I mean, how many query can make it up to this point. In particular, if I click, he shows me what the rewriting of the query will look like. So for example, for the table archive that I'm not using, okay, here, selector from archive, he says, well, the rewriting will be x0.r comment from my archive as x0. Okay, so it's just doing that. Now, as you can see, at a certain point, it dropped at 80%. Let's see what happened there. The point is that there are two tables, there are two queries that were running on table page. As you can imagine, if the table is no more there, there's not much I can do. If instead of just creating an empty table, I know that I have another copy of the table page that I kept there just in case, and it's perfectly full of all the data I need, I can just say, for example, rename some other table to that, or copy the table to page, and the system will do the rewriting. And when I go on, let's see, for example, I go at the last step, and I see here my query that run on text, and now we'll run on T1 and T2 when we make the join and go on with the selection. Now I go back to the slide for just 1 second, and I move to the to sort of I call it the mad DBA example, meaning that I guess no one really wants to do that much damage to a table, but let's assume just to test our system. So I do a decomposition as I did before, but then on one side I will partition the data horizontally. I will rename the table, rename one column, and join it with another random table. And on this side, I do a tricky thing. Basically, I take the attribute old flags, and I split it into two sub-attributes, and then drop the original table. So to go back, what I will need to do is concatenate the two sub-attributes. And on this other side, I add an attribute provenance that is needed because later on I will merge or make a union with another table which will contain some random data that I don't want. So I will use the provenance when I go back to partition the data in order to have here only the data that pertain to that table. So let's see what happens when I do this. OK. No. Let me go back to the presentation because I'm not having the screen. What's going on? OK, I will have to switch to mirror, because otherwise I don't see what you see. OK, so I go back to the SMO design. I will remove all these DDs, and I load a previous OK, test all. I don't know why I'm not seeing it. OK, and I load it. So basically, this set of SMOs are the one we've seen in the graph, and just throw in sequentially. So now I go to the inverse side, and I see what happens here. Of course, I'm doing funny things, so like dropping columns and things. So he's telling me, OK, this inverse, I'm creating just an empty column. So he's highlighting it in red to tell me you might want to do something there, make it something better than that. OK. So what I will do in this case is saying that I will create this attribute as a concatenation of split flag 1 and split flag 2. There were the two attributes that represent basically the left and right hand side of my initial old flags attribute. So what I'm doing, I'm recreating the column old flags, populating it with the concatenation of these two. And the functions are limited to run on a tuple level on the same table. And it can be user-defined function or whatever you want to put there. And let me copy here so I will be faster. And then I comment on it. So what it does here, saying that I merged the two table. And now to go back, what I will try to do is using the provenance column to decide where the tuple should go. And in this case, I will use provenance equal to old. That was the value I set for the text2 table to send the data back there. The system, in the meantime, executes all the queries throughout all the evolution step. And it seems that everything worked fine. In fact, we didn't really remove any information. We just reshaped the data into the database in many funny different ways. But we just moved data. So if we look down our table text, now it gets pretty nasty. But it's correct. I spent about 20 minutes to read this and making sure. So it seems good to me. So basically, it's concatenating the two column that has been split. He's merging the two sides of the composition on top. He's using some provenance equal to old to filter out the data that were just added randomly there. Is making a union because we had a partition at a certain point. And it's putting everything together with, for example, renamed attributes. And he's executing, doing the same job. So now, if I want to make sure, I have one tab that I call validation. Here the idea is basically I can run some extra query and make sure that everything is fine. Just for academic purposes, I'm showing here the entire set of DEDs, which is endless and horrible, that basically are the internals of the system. So the mapping between the old subsequent schema version that are used by our Mars engine. And finally, we can get to a deployment phase in which down here I generate a SQL migration script that basically will implement one SMO at a time and migrate the data through. This one is one that I was saying can be optimized because I might see that there is something that is done and then process again. And so I can make one single step there. And here I'm generating the inverted views. In particular, I want to show you the view for the text. So it's this one here. And basically, as you can see, is showing the union between the two sides and etc. Okay, so it's supporting the table text as a complex view on top of whatever it was there. And this is, of course, a composed view because otherwise I would have generated one single view and I would have a a chain of views. But too long chains of views doesn't look good into the database, so we generally decompose one directly. So, okay. This one we've seen. So current and future work in PRISM. So one thing is extending the SMOs to deal more explicitly with integrity constraints. So being able to add and remove integrity constraint and to see how we propagate integrity constraint through the existing SMOs. This will give us more better guarantees on instead of just saying, oh, this decompose might not be information preserving. If I know how I do the decompose and how the integrity constraint will be, I can make sure and give better feedback to the user, basically. And we model the update as mapping between database instances. And we are modifying the rewriting engine in order to rewrite the update as well. There are a few issues there, but it seems it's working fine.
Can you, when you find a transformation which doesn't preserve information, can you always, in some automated way, add something to the new schema which preserves the information?
I don't think it can be done always. I mean, it depends what the user wants to do. But some cases, for example, like when I did the merge, the trick that you're suggesting was there when I added the provenance column. Of course, that it's being done because I know I was going to do a merge, and I need something to go back. So in the case of Wikipedia, there was a situation like that in which I added a fake column, and then I remove it because basically later on in the schema, by comparing two existing attributes, if they were equal, I could generate, for example, 1 for the provenance column or 0 if it was not. In the case of Wikipedia, they used to store pages as current and old, and then they put them all together and split them horizontally with page and revisions. So by doing some comparison, I could understand if a table is a current one or not. And so sometimes it's possible. And I would say it's depending on what you want to do with the data. If you want to drop a table, okay, you can copy somewhere else before, but it's kind of tricky.
You want to extend the target table, you want to extend the target schema so that it has all the remaining information.
Yes.
So you can always do that. I mean, you can just duplicate any of the source stuff that was missing.
Yeah.
So the question is whether you can do it minimally.
Yeah.
There's some kind of a diff between, you imagine that you're just taking the union of the source schema, the target schema, and now you want to get rid of all the source schema stuff that's subsumed by the target schema somehow.
Oh, I got it. Okay. And future work on PRISM is the idea is extending the SMOs to cover aggregates and data to metadata transformations. So in the data we collected, this seems very rare case. I think it will be probably less rare if you have a chance to obtain ETL transformation and this kind of other scenarios. So we definitely want to extend this SMO. I think it's a needed extension. And we want to apply the query writing feature of PRISM to the problem of determining the data provenance in ETL scenarios for data warehouse. So when you have data warehouse, you use the ETL to load the data warehouse. And now we can rewrite the query that runs on the data warehouse as a query that was running on the original database. I can have an idea. I don't really want to do it because, of course, for performance reason, will not be smart. But it's just to have a clue of what's where the data were coming from. That's future work. We didn't talk much about it. It is similar to what ORCID is doing. And the other, I think, is that by having sophisticated tools that support schema evolution, you can think of a design methodology for database which is less upfront and rigid and be more like the agile methodologies for software development, something like a design as you go, in which you allow people to have to design the schema and then to keep evolving during the design because you will have better support from the tool side. So now I don't have any more the time here, so tell me if I'm going long. Now we start talking about the archival part. And so this was PRISM that support, let's say, legacy queries on top of the evolving snapshot database. And also store the historical metadata that, of course, it knows what are the schema and what are the relationship between the schema. So if we also maintain a transaction time archive of the original snapshot database, now we can think about supporting temporal queries on top of this archive. And the problem that we are under schema evolution. So we will see that this is quite challenging. And so motivation of transaction time databases, you will ask David, but I think we all agree that maintaining archive of databases might be very useful for a bunch of reasons. Now the problem will be, how can I archive and pose complex temporal queries on top of this archive that has an evolving schema? So the three challenges are how to achieve perfect archival. We said that in the evolution, the user might say drop table. And of course, I don't want to drop the entire history of that table. Otherwise, what's the point of having an archive if I drop, if I lose this piece of information? And I also want to be able to query this thing without too many troubles with the schema evolution. And there are issues for the query language I'm going to use. And achieve, of course, reasonable performance. I have a big database that keep growing, complex temporal queries, temporal coalescing, and whatever else. So that will be a challenge. Perfect archival, the idea is maintaining original schema archiving. So the data will be stored under the schema in which they firstly appeared. So this way, we do not corrupt the archive. We will need to take care of the schema evolution somewhat in an automatic way, because we don't want the user to issue queries on every version of the schema. And to achieve performance and have expressive query languages, we will decouple the logical and physical layer. And I will show you how. And we will need to plug in some extra temporal-specific optimization for removing temporal joints, optimizing temporal coalescing, and so on. So we said, sorry. So we said the schema must be the original one. In fact, if I migrate data, we said we lose information. So we want to keep the data in the original schema. Now the problem is that my entire history will be broken into a series of different schemas. And I need to support queries somehow. So one idea is that, well, the user just specify a temporal query is just splitting his query into a series of subqueries, each one of which run on a different schema version. I don't want to see the biologist of the ensemble database write 410 different queries to obtain the history of some gene or something. I don't think is a decent interface. So in literature appeared the idea of basically letting the user query one version, in this case is the last one, and to answer, we will migrate the data answer there. Again, this is good for us as a answering semantic, but it's not what we want to do in practice, because it would mean materializing the history in every version. And so what we will do is actually letting the user issue the query in one version of the schema and migrate it, and rewrite the query with similar technique, but now will be like temporal queries and things changes a little bit. So we said transaction-time databases, one of the issues was the query languages. So we need to have some expressive query language. We want to issue not only snapshot queries, but more complex queries. There have been many proposals and that tend to extend the standards. Now there's making inroad in the actual standard, SQL standard, some basic support for this. There are two competing models for transaction-time database. One is tuple-level timestamping, in which I'm basically going to add timestamps at the tuple level. So every time a tuple changes some of its attribute, I will basically create a copy of that tuple and put the new timestamp for the life of that tuple. The problem is that you create some redundancy, and when you take the projection of one attribute, you might have duplicates. If you look at D02, here we have 2 meeting time. And if I project only for that, I want to answer my user also with the information about the life of that value. I will need to collapse those two duplicates and join and unify the two time spent. While for the redundancy, there are other ways to remove it. I know ImmortalDB is doing interesting compression techniques to avoid this duplication. Still, you have the problem of doing temporal coalescing, which is a very expensive task. So the other approach is attribute level timestamping. The idea is that basically you put the attribute, the lifespan of that value to each attribute. This has been said is better in literature. The problem here is that, of course, you have less redundancy, and you don't need you need less temporal coalescing, because the idea is basically that when I filter on department number, now I already have the data represented only once. A problem is that doesn't look like a relation. It's not a relational table. It's a funny object. So how we go with it? We use XML to represent that. So before someone think I'm crazy, I want to say that I will show you what's the advantage of XML at the logical level. I'm not going to store the history of a big relational database in XML and try to execute XML queries for real.
Sounds like you've had a question on that before.
Oh yeah, plenty. So, so the idea is that we can represent a stable XML like this with we have database, table, row, and the attribute. And now the timestamping will be attributes of the various columns. So changing the value of one attribute in the tuple, in the tuple, means just adding one new element here with a new timestamp to represent this new value. So why we use XML? Also because XQuery will be our query language. And XQuery is actually a pretty good query language for when we have to express temporal data. The good two things is that complex temporal queries are reasonably simple to express. And I know Professor Zaniolo made several tests with a lot of students, and he says that they can understand XQuery way better than various SQL temporal extension. And so he definitely decided that XQuery will be the way to go. And the good thing is that you need no extension. There's no special treatment for the temporal things. So here I have a few examples. For example, the classical give me the history of the title of some given employee. It means filtering and getting one employee and then getting the title. And if you think about the previous slide, this means getting this bunch of titles here, which is exactly the history. And so other example, we can find employees. The snapshot will be basically filtering on time start and time end with a given moment in time. And I can say retrieve employee who work in the department D01 and left before a given moment in time. This will be fairly simple. I will say that the department number will be D001 and the time end will be this one. So it means that the tuple was there, the guy was working in that company, in that department and left before that moment in time. And of course we can think about more complex things like give me the people who worked in the same department of David Lomé in 1987 and now are working somewhere else. Because it's simpler to express like this. So when I do evolution, what I will do, I will rewrite this query into an equivalent query that span over the various schema versions. So here is an example. I'll move a little bit fast because I have a few slides to finish. So some rewriting performance. Let's assume we go XML first of all. The rewriting, well, pretty difficult. Meaning that now we are rewriting XQuery, so we need to use XICs, which are basically the DD equivalent for XML. And if we do not do any optimization for 100 schema version, we will have over 100 seconds of rewriting time. That's not something nice. If we prune SMOs and we do some SMO compression, we can get it down to a little bit less than half a second for 100 schema version, which is still a little bit too much, but is acceptable because it's a temporal query. It's not issued very often, so we can assume for now that that is fine. When we try to do execution, big trouble comes. We try to execute it natively. Okay, we take a bunch of queries, temporal queries that run on that, and actually, this green line means that the system crashed before the MonadDB XQuery engine crashed before giving me an answer. So we need to plug in some temporal optimization that, for example, detects the temporal joins and remove unneeded joins, and do minimum source detection, so removes sub goals in the XQuery. And this actually can make it this time. And it can go, for like 10 seconds or 12 seconds. Problem that the database is extremely small. It's not something we would want in practice. Having a history of a table which is say 640 kilobytes, it's just not reasonable. So we want to go for relational now. So we still like XQuery as a language. So our query interface would be XQuery. And what we will do, we'd actually shred the XML document into HTables. HTables are basically a relational way of representing this XML document in which you basically split the various attributes in different tables. And the idea is that now we can rewrite XQuery into SQL for those. And this is coming from the Arches system that was developed at UCLA. And once we have SQL that run on that, we can use SQL rewriting, which will be, as we see, faster, to do the version adaptation on top of the various portion of the history. Nice thing is that now we take care of the evolution at this level. It means that if we want to plug a new time version of SQL, it will be enough to have the translation from that input query language to this SQL on top of this kind of H table. And then the evolution will be taken care down there. So just to have a look to the performance, the rewriting time goes down to roughly 400, roughly 15 milliseconds, 12 milliseconds, which is definitely better than the alpha second we got before. And the execution performance, we compared Galax, which is another native XML, how DB2 deals with XML, and our H table, so our relational shredding of the XML, tuple-level timestamping, and the snapshot database. Because in fact here, the example I'm showing is a current snapshot query. There are a bunch of other graphs in the paper, but this is the example. And here, the growth goes from about 1 megabyte to about 1 gigabyte of data. So it's definitely more reasonable than what we had before. So if you see here, we have from the Galax, we have about 4 order of magnitude of improvement in executing that in this way, coupled with respect to DB2. We are very close to what the TLT can do, or even better for when the size grows, and very close to the snapshot database, which for a current snapshot query is like sort of a golden standard. Better than that, we can't go. I'm almost done. And so one other issue we were saying was temporal coalescing, so removing the duplicates with the meeting time spent. So just by moving towards attribute level timestamping to H tables, we are reducing a lot of need for coalescing. Okay, so we are about 5 times faster in queries that would need coalescing in the tuple level timestamping. But still,
because of reduced data sizes?
just because they are pre-coalesced, basically. You don't really need to coalesce anything in the attribute level timestamping, because the data are already represented only once with the overall timestamp time span that you need. So you're basically removing the need for part of the temporal coalescing.
Yeah, I was just wondering whether that was due to the fact that the data volumes were that much smaller.
Partially it's probably due to that also, and that's probably also what we can see here why we go a little bit better than the tuple level timestamping, because it's probably have a little bit less tuple to deal with. And but still, since we break the schema, the history due to the schema evolution, we still need to do some coalescing there. Because every time I change the schema, I will need to have basically a little bit of duplication of the table that were still alive in that moment in time. So we basically define a new way to do the coalescing, which exploits the characteristic of the problem. In fact, it works fine for the partitioning. It's not a general coalescing technique. And when compared to SSC, which is like the best in literature in terms of coalescing algorithm, it was developed by a previous student of Professor Zaniolo, we go a couple of order of magnitude faster than that. Again, because we are tackling the coalescing only for partitioning. Also, last slide. HMM is Story Metadata Manager. Once we understand how to use xQuery on top of the data, it's enough to have a sort of a versioned information schema, and then we can run XML queries, temporal XML queries on top of the schema history. And here's, for example, the previous, the beginning, the slide in the beginning as we get it in xQuery. So concluding, finally, PRISM support schema evolution for snapshot databases, take care of the data migration and derive logical mapping and rewrite queries. And PRIMA support perfect archival of databases under schema evolution and provide intuitive temporal queries. X queries are default. We can think about extending it with new query languages, and support query answering performance by having an architecture that split the query interface from the logical layer and support and provide some temporal optimization to run faster. If you're interested, there is demo papers, screencast, and whatever else at that website.
Thank you very much.
Can you comment on there's a bunch of languages along the way here.
Yep.
Can you comment on the expressiveness of each of them? I mean, you're handling what kinds of queries, the mappings you said are these embedded dependency language, which I assume are basically conjunctive queries plus equality. I'm not, anyway, just, and also just where do you run into trouble? I mean, if you tried to extend this to a richer, to richer queries or richer mappings, would things start falling apart?
Okay, so the queries that we support in the PRISM system are basically union of conjunctive queries. That's the baseline, and I think you can extend it probably with aggregates, I guess, without too much trouble. But we have to figure it out more precisely. Outer joins are trouble for the rewriting engine because we plan to deal with it. The problem with the outer join is that it's non-monotonic. So what happened is that the rewriting engine is sort of not dealing with the negation much. At least the same problem with the negation actually comes when we try to do updates. Because, for example, I have to say you have negation that pops in down there. And what we're trying to do is that it was basically you can use the chase in a sound but not complete way to do the rewriting. So it means that it can, if it succeeds, you basically isolate the negation. So you take whatever is inside the negation, whatever is outside the negation, you try to rewrite. And if you can come up with a rewritten query, the rewritten query will be correct. It doesn't mean there might be cases in which you cannot rewrite because it cannot deal with the negation explicitly. So we're actually implementing that right now, and the idea is basically trying to see how much not complete it is. So if it can deal with like 80-90% of the cases, it's still useful. If it deals with 5% of the cases, we cannot claim to have much. So that's one thing. The XQuery language, the query we support are basically relational queries. They're expressed in XQuery because it's nicer to talk about the temporal aspects, but that's just those are basically just relational queries on top of XQuery. In fact, if you see, we do not use the full power of XML and XQuery. There's just a specific kind of XML schema that is comfortable to be used. The advantage of doing that is not really the power because we want to use the full power of XQuery, but the idea is that there is no need for extension to XQuery. So it means that whatever optimization that will comes in for that language, it can be exploited without requiring tweaking and adaptation to this SQL, new version of SQL that we can come up with.
Do you handle all of XPath? That would be impossible, but how much of XPath?
I didn't do much testing this. This was mainly work for the other student, so I don't know exactly how much he implemented of XPath.
There are some undecidable problems buried in there when you start working.
Yeah, no, I think it's at the moment it's fairly limited. I don't know how much of that limitation are due to the fact that the guy was lazy and didn't implement the entire parser and did everything, or how much was actually a real limitation, technical difficulty. So I know the example we tested were not extremely difficult. I would say they were fairly interesting temporal queries from a temporal point of view. Not extremely challenging for XPath, but basically just filtering on top of the attributes in different ways. And the idea is that you can, using again XPath, you can define some comfortable function that, for example, check the overlap. So you just give two elements and you check tell me if they are overlapping in time. So this will make the user queries even more comfortable as a language, basically.
So I had a question about tuple versus attribute timestamping. We do this differential compression, and it's not clear to me that isn't simply a low-level implementation choice, whether you want to refer to it as tuple level or attribute level. The information's the same, right? It's just a matter of how efficiently you represent it. Isn't that right?
I guess the problem is that okay, you're doing. If I got right what you're doing, because I read the paper, but I might be wrong. You're finding a smart way to compress the data, but still conceptually that's tuple level timestamping. So you still have one attribute would appear several times, but actually it's being compressed just for performance reasons.
That's right.
But the moment in which you have to return the user, if you limit to snapshot queries, will probably make no difference. But the moment in which you want to return, either doing more complex queries that need, for example, temporal join, or if you want to do queries that return to the user the time life of that attribute, at that point, with tuple level timestamping, no matter how you implement it, I think you need to find the duplicate and see how many times that tuple existed and get the time span. While in the attribute level timestamping, that is not needed because you only have the attribute is only once, appears only once with the full time span already written there.
Yeah, so if I can translate that, I think you're conceding that the information is there, but the way to express the queries is harder in one view than it is in the other.
More than not only the way you express the query, but especially the problem when you compute the query. Because when I have to compute the temporal coalescing, let's say you have whatever language is on top and tell me, just do temporal coalescing, do this projection and do the temporal coalescing there. Because I want to know for how long the guy worked in the department. At that point, in one case, you have the attribute with directly the information there. I just have to throw out the attribute time start and time end, and it's already what I have there. In the other cases, you have the attribute will appear multiple times. From storage issues, you might have squeezed the representation of the value of the attribute, but I think you still have the multiple timestamp in which the query went, the tuple went through.
Operator that operates directly on the compressed representation. Yeah.
I guess you can go in that direction. Actually, what we are doing also for the temporal coalescing, it was basically when we split due to the partitioning over time, we basically maintain one extra attribute that tell us where this data was coming from in the previous version of the schema, plus some other extra metadata around there. But the idea is basically, and I think you can do probably something similar, saying that I don't only have the timestamp for the entire tuple, but somehow a reference to where is the timestamp for this attribute, or something like this. Definitely you can think something like that.
So, changing the subject, there's querying across time, of course, is complicated by schema evolution. And, you've got nice stuff here, but there's an equally big problem of data evolution that needs to be solved.
Say it again?
Data evolution. So the fact that, I've got some genetic database and they changed the gene name in 2006. Or, in my company, we used to have winter reviews, but then we opened an office in New Zealand, and so now they're called January reviews because, it didn't make sense. And so, I'm not sure what my question is, but it seems like it'd be interesting to think about how do you sprinkle in, equivalent statements about data, as well as equivalent statements about schema, so that you can, I want to get all the history of the information about this gene, including that.
This is the point we changed the name for the gene.
Including that under the previous name or something.
Okay, I think there's one option for doing that. At least it's linked. It's not meant exactly for that, but somehow can be changed to work that out. When we do the add column, for example, we can add column with using some function to populate it. So what you can think of doing is something like I add a column and I generate the value inside that column by some transformation function that takes gene A and call it gene B. And then you have, of course, the drop column and the inverse. So in the query, you will have something like up to a certain point, the queries will just ask the column, whatever it is, the name of the column. And from a certain point on, we'll ask that column. And whenever they mention it, we'll run a function on top of that. So say my query starts saying select gene name equal gene A, and this will be through up to a certain point in history. From there on, the subqueries will say something where gene equal change name to gene A. Okay, something like this. That's something I think you can think of doing. I don't know how much can harm performance because we'll start like issuing functions and function calls throughout the execution later. So that becomes.
That function might have an extensional representation too,
That's actually that's the way we deal with function through the rewriting engine. We take the function representation. We say, okay, let's assume there's a table that implements this function. We do the rewriting, assuming it's a table. And at the end, we say, okay, that was the table that we just and we call it back into a function call. So definitely you can think of doing something like that as well. And I think it's
what translates this data evolution into a schema evolution, basically, or at least to a temporal schema.
Yeah, in that sense.
I think that's right. It's promoting it up to saying, rather than having Yeah, you say there's a new column that has the new names, and so now it's,
That's similar to the problem of when you want to do pivot and unpivot. At the moment, we can sort of support it by saying you add column based on how many different value you have inside. But of course, it's not the way to go. I know there is some interesting work by Tan in Wanchu Tan and other people that work at UCSC and IBM to basically having they use some technique basically to deal with this. And the idea is that probably when we want to extend SMOs in that direction of data to metadata transformation, we might also try to tackle this problem you were suggesting and try to see what to do. Or maybe we can have some extra integrity constraint that we can plug into the system that speaks about the value and says, for example, whenever we say gene A is equal to gene B or something like this, and then use the rewriting engine to do the magic in the query as well.
We should probably wrap up that, but I want to thank you very much. It's an interesting talk.
Thank you very much.